Thank you for the introduction. So my name is Pandurevic, Dominik. I'm working at University of Innsbruck in Halle as a junior scientist and PhD student at the Institute for Measurement and Sensor Technology. And today I would like to speak about a method for the analysis of speed climbing runs with the usage of feature detection algorithms. So I would like to start my presentation with some slides describing why I'm doing such things and why the climbing sport needs such innovations. So most of you know that the population of the climbing sport in the last 2 decades has increased rapidly. So here I have some examples. So in this image you can see the Boulder World Cup in 2000. So the third Boulder World Cup with just a handful of visitors. And compared to that, the 20th Boulder World Cup in 2018, so about 20 years later, where you see a full stadium celebrating and cheering for their athletes. And of course, the attendance or participation at the Olympic Games in Tokyo 2021, as well as the participation in Paris 2024, reaches the peak of the popularity and media attention, and therefore also the increase of the popularity results in raised requirements for elites and trainers. Again, we have these two Boulder World Cups. So on the left side, you see very static movements. There you can also see the modification of the rock climbing, which bouldering is. And on the right side, you see, compared to that, very dynamic motions, including jumps, which requires, of course, very high motoric skills, as well as good timing, and therefore you need other training methods to train for such events. So in sport climbing, we have the three disciplines: bouldering, lead, and speed climbing. At the participation in Tokyo for the first time, we had a combined discipline where every one of this discipline was combined, and this decision was never accepted by the climbing society because bouldering and lead are very similar. You can train for that, but if you compare it to speed climbing, there are no comparisons, and it's very hard for a lead or a climber to train for a speed competition. So luckily for the Olympic Games in Paris 2024, there will be two disciplines. So one combining boulder and lead, and one separated one for speed climbing. And today I would like to talk about a method where I analyze a speed climbing run and such parameters only with the usage of the recording and without any physical sensors. So here, this image demonstrates the method from bottom up. So on the left side, you see the illustration of the recording. So we have one specific camera setup for every competition. So the camera is placed in a current tape, has a specific distance to the wall and a specific focal length, and it is tilted upwards to follow the two climbers in speed. What we do then, we take the recording, take the single frames, and we try to transform the one recording, which has these specific parameters, into a common coordinate system. And therefore, we are looking for some motion. So we are detecting random features on the images and trying to detect the movement of the camera in the image or in the recording and the frames. Then we are using, we're trying to locate specific objects like the climbing holds to get a scale factor where we can transform the image plane to a wall coordinate system, and therewith we can calculate, for example, the speed of the camera. And with the speed of the camera, we can subtract it from the speed of the climber, and then we get an absolute movement of the climber. And therewith we can get comparable data. So if we have recordings with the same coordinate system, we can transfer this to a comparable data set, and then we can compare different athletes from different recordings. So here again the summary. So what we are doing some image processing and feature detection, where we detect the speed athlete, random features, and the holds on the images. Afterwards, we are able to calculate the movement of the camera, the scale factor, and some correction factors. And at the end, we can calculate important parameters like the velocity or contact time or any parameter in any single ball section. So for in the first step, we are trying to detect the human body skeleton. So we are using open pose. Here you can see example. So we feed it with a frame, and then we get the position of every key point of the human body skeleton for both athletes. In the next step, we are using an algorithm called clamp points, which detects random features on every frame. So from frame to frame, the same feature, and tries to match it. So while we are doing this, therefore, we get these distances. So you see an overlay of two frames, so one frame after the other, and we get the distance of the moved feature in the frame. So therefore, we can get the movement of the camera in X and Y axis, and therefore we can calculate the absolute speed of the climber. And in the last step, we take we use a neural network for object detection called YOLO. It is pre-trained, and what we are doing is we're feeding it with images where we manually marked the holds on the images. And as a result, after feeding the neural network, it starts learning the position of a hold on an image, on any image. So you can imagine feeding it with more images will make it more accurate, and we will get better results for detection. So you can see here on the speed climbing wall, we have one specific climbing hold, which is 20 times mounted on the wall in specific directions. So it not only detects the position of the hole, but also the number of the holes, which has some features on the image, and it's therefore for the neural network it can recognize it. So then we, as every speed climbing wall on the wall is standardized, we can take the distances of one hold pair. So we have the X and the Y distance of the hold pair, and we can compare it with our detected holds, and can then calculate the scale factor from our image plane to our wall coordinate system in meters or meters per second or whatever. And here you can see then the calculation of this scale factor. So we're doing this over the whole recording to get a course of the speed of the camera. As you can see here, the speed, as you know, the camera is following the athletes, and therefore it's changed the velocity because of the speed climbers. Yeah, here you have some results, what you can do with it. So we have two climbers with different techniques in the start, and we are analyzing, for example, the velocity of the center of gravity in every wall section, and can see, for example, the transfer from the start section to the middle one section or whatever. Additionally, I programmed a user interface, which can be used which is used by trainers and athletes. So you get an Excel file as a result from our algorithm. You can load it inside of the interface, and then you get multiple parameters which you can compare. For example, the velocity of the center of gravity. Additionally, on the right side, you can see the path of the center of gravity and the speed. And therefore, you can compare different athletes. For example, you can take a world record holder and compare it with an athlete from a national team or whatever. So we are cooperating with the Austrian national team and therefore using also some data from them. Okay, some quick conclusion because my time is over. We take the recording, we have the climbing process. Through image processing algorithms, we get a comparable data set, which we visualize with our interface. And afterwards, of course, we need the experience of the trainer and the athletes to evaluate the results. Here are also some future work I'm working on. So we are feeding a big database by feeding it with a lot of recordings of speed climbing competitions and trainings, and therefore we're trying to make some statistical analysis. Yeah. So thank you very much for your attention.
Thank you, Dominik. Any questions?
Can you explain me more in detail how the error is different when the camera is looking at the bottom and the top according to the parallax? How do you correct or estimate this error? Because the parallax is not the same when you are looking to the top in comparison to the bottom.
Yeah, of course. So we do this clamp point algorithm is calculated from frame to frame. So we're taking the whole recording and calculating the position for a scale factor. We take the neural network. So for every frame, we're detecting the holes, and we don't have just one hole. We have a lot of hole pairs in one image, and then we take the mean of these distances in X and Y, and therefore we get the scores. And of course, we have this error, and we are then fitting it with different algorithms to get a smooth movement of the camera, because, as you know, the camera is trying to move smooth for the visitors.
How the panning is made to be smooth?
Sorry?
How the panning to go from the bottom to the top is performed to be sure that it's smooth motion.
It's performed by cameraman.
Yes, but the way he's doing that, it's so quick that we don't know how the cameraman is doing well or not.
That it depends also on the camera, because there are some the setup is so constructed that the cameraman is just moving the camera, and the calibration of the image and some errors are after them filtered. But I don't know about the recordings. We are just taking the recordings and then getting the results. Yeah,
it's just to know if, for instance, if you had a second camera filming from the top and mixing those two images, would be a value add or not especially?
Yeah, of course. If we would have that, the thing is we are measuring in 2 dimensions, only in X and Y. So if we would have a better camera system set up with more than one camera, then we could, for example, measure the 3rd dimension and get more precise images. But we are just trying to take the recordings and get results out of it.
Okay. And just for your interest, there is a recent application doing the same that we do, but with a drone.
I know. Yeah.
In frontiers, maybe you know.
I know.
Yeah. Thank you very much.
Any other questions? Time for a quick one. Yeah.
Just a very simple one. Does the time from when they set off to the top match the time that they deposit?
Yeah, we're also doing this for this statistic at the end. So it's a kind of filtering. We are trying to analyzing all the recordings and also calculating the end time, which would result from our results, from our parameters. And the good ones are still in the database, and the other ones are filtered out. So of course, we have some errors, but we are trying to just take the good ones, where the end time of the real end time corresponds with our calculated end time.